Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad Anas Nur Akasha bin Mat Mustafa. My numeric is AD220072. I am from Group 3 for Mini Project Electric and Electronic Technology. So our group is make water level indicator. I will present the introduction for water level indicators. So water level indicators are crucial device for measuring and monitoring water levels in various applications, such as tanks, reservoirs, and wells. They are essential in controlling overflow, monitoring water usage, and ensuring effective water resource management. The Water Level Indicator project aims to develop and build a dependable and cost-effective system for measuring and displaying water levels in a specific container or system. The design and construction of the Water Level Indicator project require careful planning and consideration of unique requirements, such as ideal water level threshold for signal, circuit design, and power consumption. Factors such as resistor, transistor, a buzzer, LEDs, and terminal connection are essential. This project can be effectively completed by following a methodical strategy, providing an efficient solution for water level monitoring. For the background of the product, the water level indicator is a crucial tool in monitoring and managing water resources. It provides real-time information about the water level in various settings such as tanks, reservoirs, and rivers. Accurate water level monitoring is essential for effective decision-making in flood control, irrigation system, and water supply management. Conventional water level indicators have limitations in terms of accuracy, reliability, and compatibility with existing system. These projects aim to develop and improve water level indicator with enhanced performance and functionality. The usage of these components enable for a small and cost-effective water level indicator that use electrical conductivity and resistance principle to correctly monitor water levels and offer visible or aural feedback. When the water level exceeds a preset level, the buzzer sound inaudible alarm, allowing timely action to be done. LEDs give visible indicator, allowing user to analyze the situation rapidly. So, for the problem existing for the application, several challenges are associated with the application of conventional water level indicators. Firstly, accuracy is a significant concern as minor deviation in water level measurement can lead to substantial errors in water management decision. Secondly, response time is critical in detecting rapid change in water level, particularly in flood monitoring scenarios. Delays in detecting and signaling such change can lead to significant damage and safety risks. Thirdly, reliability is essential to ensure continuous and uninterrupted operation in various environmental conditions. Conventional indicators may be prone to failures, compromising their effectiveness in critical situations. Lastly, compatibility with existing system and protocol is crucial for seamless integration into water resource management frameworks. So, our group objective is first, to design and develop a new circuit for a water level indicator with improved accuracy, response time, reliability, and compatibility. Second, to assess and analyze the performance of the proposed water level indicator in comparison to conventional indicator. Third, to evaluate the accuracy of measurement obtained from the indicator through the comparison with reference measurement. Fourth, to measure the response time of the indicator in detecting and displaying changes in water level. 5. To test the reliability of the indicator under varying environmental conditions. 6. To assess the power consumption of the indicator for energy efficiency. 7. To evaluate the compatibility of the indicator with existing system and protocols. And lastly, to draw conclusion based on the assessment and analysis and provide recommendation for further improvements.
Right now I'm going to present about 2.0 materials and component. There are 5 materials and component that was used in this project. First of all is 2.1 resistor. A resistor is an electrical component that resists the flow of electric current in a circuit. We'll be using it in our water level indicator to limit the current flowing through the LED and the transistor. There are different type of resistor available on the market, but for this project, we are using 100 ohm resistor. Secondly, 2.2 transistor. A transistor is a semiconductor device that can amplify or switch electronic signals. In our water level indicator, we'll be using to switch on and off the buzzer and LED as the water level change. The type of transistor we'll be using is a NPN type called NPN PN2222. Thirdly, 2.3 buzzer. A buzzer is an electromechanical device that produces a buzzing sound when activated. It will be used in our water level indicator to alert us when the water level reach a certain point. For this project, we'll be using a 5 volt DC or direct current. 2.4 LED or a light emitting diode. LED is a semiconductor device that emits light when an electric current passes through it. We'll be using LEDs in our water level indicator to indicate the current water level. We'll be using different color LEDs, green for when the water level is normal, blue and yellow for 3 and 2, and red for when the water level is too high or too low. Lastly, 2.5 wires and terminal connectors. We also need wires and terminal connectors to connect the component together and form the circuit. Make sure that you use wire of proper thickness, as using inadequate thickness of wire might result in undesirable heating up or burning up the wires. That's all from me.
Assalamu alaikum and hi everyone. My name is Salman Dahir Mahmoud and my matric number is BD220004. And in this part of the presentation, I'm going to talk about the methodology of our project. The circuit design of a water level indicator is critical for its operation and accuracy in monitoring water levels. It's made up of several components that work together to create the intended result, such as resistors, transistors, buzzers, LEDs, and terminal connectors. The resistors are deliberately positioned to form voltage dividers, ensuring that the voltage across each resistor matches to the observed water level. Based on the detected water level, the transistors operate as amplifiers and switches. Regarding regulating the buzzer and LEDs, when the water level reaches a specific level, the transistors activate the buzzer, which emits an radio alarm and regulates the lighting of the LEDs, which provides a visual indicator of the water level. As for the terminal connectors, they built up into the circuit designed to make installation and connecting to the water system as simple as possible. These connectors provide secure electrical connections that enable the indicator to receive input signals and produce reliable readings. The schematic diagram, which depicts the connections between the various components aids in understanding the circuit setup as well as troubleshooting and modification. A steady and efficient system for water level monitoring and controlling is created by combining the resistors, transistors, buzzers, LEDs, and terminal connectors. Next will be the circuit design and diagram. The methodology of this project involves the development and implementation of a new circuit design for water level indicator. The circuit design incorporates resistors, transistors, buzzer, LEDs, and terminal connectors to achieve enhanced performance. The new circuit design focuses on improving accuracy, response time, reliability, and compatibility with existing systems. The circuit components are carefully selected and configured to ensure optimal functionality. And this is the circuit we have built up using Proteus software. Thirdly would be component selection. The specifications, performance, characteristics, and compatibility of each component are carefully considered during the component selection process. The objective is to select high-quality components that fulfill the water level indicator circuit's specifications, ensuring its dependable and efficient performance. The component selection section focuses on the major components used in the water level indicator, which include resistors, transistors, buzzers, LEDs, and terminal connectors. It describes the criteria used in the selection process, such as resistance value, power rating, voltage requirements, sound output level, LED characteristics, and connection compatibility. The emphasis is on selecting components that match the circuit's unique needs and contribute to the water level indicator's overall performance and usefulness. Fourthly will be the circuit assembly. It's simply showing the steps we have used to assemble the components and onto the PCB layout. First, we started with placing the breadboard on clean and stable safe surface. Insert resistors into the breadboard, insert transistors into the breadboard also, and then connect components using connecting wires. And afterwards, insert buzzers and LEDs into the breadboard, and finally connect terminal connectors to the breadboard. And in the PCB assembly, we have prepared the PCB by ensuring it's clean and free from debris. And then we soldered resistors onto the designated positions. Also, we soldered transistors onto the designated positions on the PCB. And afterward, we soldered the buzzers, LEDs, and terminal connectors same onto the PCB, following the circuit diagram which we have built up already. And afterwards, trim excess wire leads and inspect the PCB for any soldering errors. And perform continuity and functional tests to verify proper connections and functionality, and finally verify absence of short circuits and errors. And here are the setup we have built up after assembling the components into the PCB layouts and connecting into an electricity. And the video is next words.
Shut up, count your calories. I never look good in mom jeans. Wish I was like you, blue eyed Bonnie, perfect body. Maybe I should try harder. You should lower your expectations. I know with your Barbie. I was never cut out for prom queen. If I get more ready, do you think he will like me?
The fourth part of the presentation of this project will be method of assessment and analysis. And first, we have used a technique called theoretical framework. In this phase, the underlying theories and principles related to the water level sensing and electronic circuit design are studied and applied. This includes concepts such as voltage dividers, transistor switching, and signal conditioning. Theoretical calculations and simulations may be performed to analyze the expected behavior of the circuit under different conditions. Secondly, we have used performance evaluation technique. The performance of the water level indicator circuit assessed through experimental measurements and observations. The circuit is connected to a controlled water system, and its response to varying water level is recorded. The accuracy, sensitivity, and stability of the indicator are analyzed and by comparing the actual water levels with the corresponding readings obtained from the circuit. Thirdly, we have used data analysis. Collected data is analyzed to extract meaningful insights and draw conclusions. Statistical analysis techniques such as regression analysis can be applied to determine the relationship between the measured water levels and output readings of the circuit. Any deviations or discrepancies between the expected and observed values are carefully examined and interpreted to identify potential sources of error or limitations in the design. Fourthly, we have used performance optimization. Based on the analysis results, modifications or optimizations may be proposed to enhance the performance of the water level indicator circuit. This could involve adjusting components values, defining calibrations techniques, or incorporating feedback mechanisms to improve accuracy and reliability. The impact of these modifications on the overall performance is evaluated through further testing and analysis. The fifth technique we have used is comparative analysis. To assess the effectiveness of the developed circuit, comparative analysis may be conducted. This involves comparing the performance of the water level indicator with existing commercially available systems or alternative circuit designs. The key parameters will be cost and power consumption, ease of installation, and accuracy, which are considered to evaluate the competitiveness of the proposed solution. That's all for me, and thanks.
Start.
So next, we'll talk about result and discussion. So accuracy of measurement. To evaluate the accuracy of the water level indicator, a comparison was made between the measurement obtained from the indicator and the reference measurement obtained from a water level monitoring system. The data collected from both sources were analyzed and the mean absolute error (MAE) was calculated. Table 1 presents the comparison between the indicator measurement and the reference measurement for different water level. The MAE values indicate the average deviation between the indicator readings and the reference values. The water level indicator demonstrated a high level of accuracy with MAE values ranging from 0.5% to 2.0%. So this is a table 1 that show comparison of indicator measurement with reference measurement. Okay, next, response time. The response time of water level indicator was evaluated by measuring the time taken for the indicator to detect and display change in water level. The response time was determined by measuring the delay between the actual change in water level and corresponding change displayed by the indicator. Okay, this table 2 shows the response time of the indicator for different water level change. The average response time was calculated by taking the mean of multiple measurements. The water level indicator exhibited a fast response time with an average delay of less than 2 seconds. Okay, so this is table 2 that show response time of the water level indicator. So next, reliability. The reliability of the water level indicator was assessed by subjecting it to continuous operation for an extended period. The indicator was tested under varying environmental conditions, including temperature variation and exposure to moisture. Table 3 presents the result of the reliability test, indicating the percentage of successful operation over a 30-day testing period. The water level indicator demonstrated a high level of reliability with a success rate of over 95%. So this is table 3, reliability test result. Okay, next, power consumption. The power consumption of the water level indicator was measured to assess its energy efficiency. The indicator was connected to a power source and the current draw was recorded at regular interval. Table 4 present the power consumption data in the indicator. The average power consumption was calculated by taking the mean of multiple measurements. The water level indicator exhibit low power consumption with an average draw of 2.05 ampere. 0.25 amperes. Sorry. Okay. The last one is compatibility. The compatibility of the water level indicator with existing system and protocol was evaluated by integrating it with different water management system. The indicator was successfully connected to various data logging system and display seamless compatibility. taking into account container size and type, mounting choice, environmental compatibility, connectivity option, and scalability will enable compatibility with a variety of water storage container and situation. Design the water level indication system to suit several container types such as cylindrical, rectangular or irregular forms, and to provide for mounting flexibility to conditions such as humidity, dust and sunshine. Select connector and interface that are compatible with conventional electrical system and, if appropriate, communication protocols. Scalability should be considered while designing the water level indication system, allowing for easy extension or connection with addition, sensor or monitoring equipment. The water level indication system becomes more adaptable by assuring compatibility with various container size, mounting choices, ambient condition, connectivity option, and scalability. So that's all.
So, in conclusion, the assessment and analysis of the water level indicator revealed promising results. The indicator showcased high accuracy in measurement, fast response times, reliable operation, low power consumption, and compatibility with existing system. The proposed new circuit design proved effective in addressing the problem associated with conventional water level indicators. The finding of this project contribute to the development of more robust and accurate water level indicators, which can significantly enhance water resource management and decision-making processes. The improved performance and reliability of the water level indicator make it a valuable tool for various applications, including flood monitoring, irrigation system, and reservoir management. Further research and development can focus on optimizing the circuit design for specific environments and exploring wireless communication capabilities to enable remote monitoring and control of the water level indicator. The recommendations are meant to improve the water level indicator system usability, accuracy, and performance. In terms of calibration, signal processing, power management, wireless communication, user interface, and connection with smart home automation, they provide proposal for future advancement. This suggestion can help the water level indicator work better, be more efficient, and have a wider range of application. The following are the recommendations for the project on water level indicators. Implementing a calibration method will help to reduce measurement errors and improve the water level indicator overall accuracy. Power management to extend the water level indicators working life, improve power management, visualization, and user interface. The water level indicator systems, user interface, and visualization should be improved. That's all from our group. Thank you.